Welcome to the Deep Dive. Today we're tackling a listener request, exploring the mind-boggling world of physics and astronomy.
Oh, cool.
You've sent us a fascinating chapter called The Science of Astronomy by Ramesh Dingana.
Great.
So buckle up, because we're about to break down some truly fundamental concepts that govern how objects move in space.
It's going to be a wild ride for sure.
Yeah.
These concepts are the building blocks of our understanding of the universe.
Yeah.
From the smallest particles to the largest galaxies.
All right, let's dive in. The chapter kicks off with speed, velocity, and acceleration, which might seem pretty basic, but
Yeah.
I'm guessing there's more to it than meets the eye, right?
You're absolutely right. It all starts with understanding how things move.
Okay.
Speed is just how fast something is going, but velocity adds in the direction of that movement.
Yeah.
So two cars could be traveling at the same speed, but have different velocities if they're going in different directions.
Okay, that makes sense.
Yeah.
So where does acceleration fit into this picture?
Acceleration is any change in velocity,
Right.
which means either speeding up, slowing down, or changing direction.
Nope.
Think about it like this. Even if a car is maintaining a constant speed while going around a curve,
Right.
it's still accelerating because its direction is changing.
So even though the car's speedometer might be steady,
Mm-hmm.
it's technically still accelerating because it's changing direction.
Exactly. And this concept of acceleration is crucial for understanding how objects move in space,
Right.
particularly when it comes to orbits and the forces at play.
Okay, this is already starting to make my brain spin a little.
Just wait, it gets even more fascinating.
Oh boy.
Let's move on to Newton's laws of motion.
Okay.
These three laws essentially govern how all objects move, both here on Earth and out in the vastness of space.
So these are kind of a big deal in the world of physics.
Absolutely, they're foundational.
Yeah.
Let's start with Newton's first law of motion, which is often called the law of inertia. Basically, it says that an object at rest will stay at rest, and an object in motion will stay in motion at the same speed and in the same direction, unless acted upon by an outside force.
Hold on, so if there were no forces acting on an object, it would just keep moving forever?
Yep.
Like a spaceship flying through space?
You got it. In the vacuum of space, where there's no friction or air resistance, that spaceship would just keep going.
Wow.
In a straight line at a constant speed, unless something like gravity
Right.
or a collision changed its course.
Okay, so inertia is essentially an object's resistance to changing its motion.
Precisely. Think about it like this. If you're standing on a bus that suddenly stops the thing, your body wants to keep moving forward.
Uh-huh.
And that's why you might stumble.
Yeah.
Your body has inertia.
Yeah.
It wants to stay in motion.
That makes so much more sense now. And speaking of forces, let's move on to Newton's second law of motion.
This one gets into the relationship between force, mass, and acceleration.
Okay.
It states that the force acting on an object is equal to its mass times its acceleration. Basically, it takes more force to accelerate a heavier object than a lighter one.
So if I push a shopping cart with a certain amount of force, it's going to accelerate faster than a cart full of groceries
Exactly.
because the full cart has more mass.
That's Newton's second law in action.
Wow.
And it applies to everything from a rocket launching into space to a ball rolling down a hill.
Right.
Force is what changes the motion of an object.
This is starting to feel like one of those aha moments where everyday things suddenly make more sense.
That's the beauty of physics. It's all around us.
Yeah.
Now let's tackle Newton's third law of motion.
Okay.
This one is probably the most well-known.
Okay.
For every action, there is an equal and opposite reaction.
Okay, so like when I jump,
Huh.
I'm pushing down on the ground and the ground is pushing back up on me
Yeah.
with the same amount of force.
Precisely. It's like a cosmic dance of forces. If you push against a wall, the wall pushes back on you with an equal and opposite force. That's why you don't go crashing through the wall, and the wall doesn't come crumbling down on you.
Wow. I never thought about it like that before.
Yeah.
But it makes so much sense. So forces always come in pairs.
Always. And this principle applies to everything,
Wow.
from the interaction of particles in an atom to the movement of planets and stars.
I'm starting to see how interconnected all these concepts are.
Yeah.
But before we move on to something else, I want to touch on something else mentioned in the chapter, conservation of energy.
Okay.
That seems pretty fundamental, right?
It is.
Okay.
The law of conservation of energy states that energy cannot be created or destroyed,
Right.
only transform from one form to another.
Okay.
This means that the total amount of energy in a closed system always stays the same.
So like if I have a ball at the top of a hill,
Right.
it has potential energy because of its position.
Mm-hmm.
And when it rolls down the hill, that potential energy is transformed into kinetic energy, the energy of motion, right?
Exactly.
Okay.
And as the ball rolls back up another hill, some of that kinetic energy is converted back into potential energy.
Yeah.
The total amount of energy in the system remains constant, even though it's changing forms.
Okay. I'm starting to see how this conservation idea applies to energy.
Right.
But the chapter also mentions conservation of angular momentum.
Uh-huh.
How does that work?
Angular momentum is a bit more complex, but it's basically the measure of an object's tendency to keep rotating.
Okay.
Just like energy, angular momentum is conserved, it can't be created or destroyed.
Right.
Only transferred.
So if a figure skater is spinning with their arms outstretched,
Right.
and then they pull their arms in close to their body, they spin faster.
Exactly.
Wow.
By bringing their mass closer to their axis of rotation,
Okay.
they decrease their moment of inertia, which causes their rotational speed to increase
Right.
in order to conserve angular momentum.
That's a great example. And this principle applies to things in space too, right?
Absolutely. It's a key factor in understanding the formation of stars and planets.
Right, as well as the dynamics of galaxies.
Okay.
Think about a collapsing cloud of gas and dust
Right.
that's forming a star.
Uh-huh.
As the cloud shrinks, it spins faster and faster because its angular momentum is conserved.
Okay, so we've covered quite a bit of ground already, from speed, velocity, and acceleration to Newton's 3 laws of motion and the conservation of energy and angular momentum.
Yeah, we have.
It's amazing how these concepts underpin our understanding of everything in the universe.
It's just the tip of the iceberg. There's still so much more to explore.
Right.
And it only gets more fascinating from here.
All right, I'm ready for more. Where do we go next?
Let's delve into the force that shapes the universe, gravity.
Okay.
We'll start with Newton's law of universal gravitation,
Play.
which revolutionized our understanding of how objects attract each other.
Okay.
And then we'll explore Einstein's theory of general relativity, which takes our understanding of gravity to a whole new level.
Sounds amazing. Let's do this. Okay, I'm ready to tackle gravity. Where do we start?
Let's begin with Newton's law of universal gravitation.
Okay.
This law basically states that every object in the universe attracts every other object.
Right.
With a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers.
Okay, that sounds pretty complicated.
Sure.
Can you break it down for me?
Imagine you have 2 bowling balls.
Okay.
The more massive the bowling balls are,
Mhm.
the stronger the gravitational force between them will be.
Right.
And the farther apart they are, the weaker the gravitational force between them will be.
So it's like a cosmic game of tug-of-war where mass and distance are the key players.
That's a great analogy.
Cool.
And this law explains why planets orbit stars,
Yeah.
moons orbit planets,
Right.
and even why the tides rise and fall.
So gravity isn't just about things falling down.
Right.
It's about this invisible force of attraction between all objects with mass.
Exactly. It's the glue that holds the universe together.
Why?
Shaping the structure of galaxies and guiding the motion of celestial objects.
This is making me think about those mind-blowing images from space telescopes, those swirling galaxies and star clusters.
Yeah.
It's incredible to think that gravity is the architect of all that cosmic beauty.
It's truly awe-inspiring. Now, while Newton's law of universal gravitation was groundbreaking,
Uh-huh.
it doesn't tell the whole story.
Okay.
That's where Einstein's theory of general relativity comes in.
Okay. I'm ready to have my mind blown. What is general relativity all about?
Einstein's theory revolutionized our understanding of gravity
Right.
by proposing that it's not actually a force, but rather a curvature of space-time caused by the presence of mass and energy.
Wait, hold on.
Yeah,
Curvature of space-time. I'm having trouble wrapping my head around that.
I know, it's a mind-bending concept.
Yeah.
Imagine a bowling ball placed on a trampoline.
Okay.
The bowling ball causes the trampoline to sag,
Uh-huh.
creating a dip.
Right.
Now imagine rolling a marble across the trampoline. Instead of traveling in a straight line,
Right.
the marble will curve towards the bowling ball, following the curvature created by its mass.
So massive objects like stars and planets create these dips in space-time.
Exactly. And it's this curvature of space-time that we experience as gravity.
Yeah.
Instead of thinking of gravity as a force pulling objects together,
Right.
Einstein's theory suggests that objects simply follow the curves in space-time created by the presence of other massive objects.
So Earth isn't being pulled toward the sun by some invisible force, but rather it's following a curved path in space-time created by the sun's mass.
Precisely. It's a completely different way of thinking about gravity.
Wow.
But it has been incredibly successful in explaining a wide range of phenomena
Okay.
that Newton's theory couldn't fully account for.
Like what kinds of phenomena? Give me some examples.
Well, for example, general relativity accurately predicts the bending of light around massive objects,
Oh, wow.
which is known as gravitational lensing.
Right.
This bending of light allows us to observe objects that are located behind massive galaxies or black holes.
So gravity is acting like a cosmic magnifying glass, allowing us to see objects that would otherwise be hidden.
Exactly.
Mm.
And general relativity also explains the subtle shifts in the orbits of planets, like the precession of Mercury's orbit,
Okay.
which couldn't be fully explained by Newton's theory.
It's incredible how Einstein's theory, which was so radical at the time,
Yeah,
has become such a fundamental part of our understanding of the universe.
for sure.
But before we go any further, I want to rewind a bit and touch back on something we discussed earlier.
Okay.
Escape velocity.
Right.
How does that tie into all this?
That's a great question. Escape velocity is the speed an object needs to reach
Right.
to escape the gravitational pull of a planet or star.
Okay.
And it's directly related to the mass of that planet or star and the strength of its gravitational field.
So the more mass of the object, the higher the escape velocity.
Exactly. Think about trying to launch a rocket from Earth. It takes a tremendous amount of energy to reach escape velocity
Wow.
and break free from Earth's gravitational pull.
Right.
That's why rockets are so massive and powerful.
This is really making me appreciate all the calculations and engineering that go into space exploration.
Yeah.
It's not just about building a powerful rocket.
Right.
It's about understanding the fundamental laws of physics and using that knowledge to overcome the challenges of gravity.
Absolutely. And escape velocity also plays a crucial role in the formation of black holes.
Okay, well, we have to talk about black holes. I find them utterly fascinating and a little bit terrifying.
They are both fascinating and awe-inspiring. Black holes are regions of space-time where gravity is so strong that nothing,
Right.
not even light, can
Ooh,
escape.
Not even light.
Nope. The escape velocity of a black hole is greater than the speed of light,
Wow.
which is why nothing can escape its gravitational pull.
Right.
And black holes form when massive stars collapse at the end of their lives, creating a region of space-time with an incredibly high density.
So they're like cosmic vacuum cleaners, sucking up anything that gets too close.
In a way, yes. Anything that crosses the event horizon,
Right.
the boundary around a black hole,
Okay.
is doomed to be pulled in and crushed by its immense gravity.
It's mind-boggling to think about all that matter and energy being compressed into such a small space.
Yeah.
It really challenges our understanding of the nature of reality itself.
It certainly does. And black holes are still one of the most mysterious and intriguing objects in the universe.
Right.
And scientists are constantly learning more about them.
It's incredible to think that these objects, which were once considered purely theoretical,
Yeah,
have now been observed and studied in great detail.
it is.
And it all stems from our understanding of gravity and the fundamental laws of physics.
For sure.
This is all so fascinating. I'm already feeling like I need to go back and listen to this entire episode again to let it all sink in.
It's a lot to take in, but it's all connected.
Okay, so we've covered a lot of ground so far. Newton's law of universal gravitation, Einstein's theory of general relativity, escape velocity, black holes. What else is there to explore in this chapter?
There's still more.
Yeah.
Let's delve into some of the fascinating consequences of these concepts,
Okay.
like tidal forces and the Roche limit.
Okay. I'm ready to keep diving deeper into the mysteries of the universe. All right, we're back. And I'm ready to tackle tidal forces and the Roche limit.
Okay.
Those sound like some pretty intense cosmic phenomena.
They certainly are. Tidal forces are a consequence of the differential gravitational pull exerted by one object on another.
Okay.
It's all about how gravity's strength changes with distance.
Okay, can you elaborate on that a bit more?
Sure.
I'm not sure I fully grasp what you mean by differential gravitational pull.
Imagine the Earth and the Moon.
Okay.
The side of Earth that's closest to the Moon experiences a stronger gravitational pull from the Moon
Right.
than the side of Earth that's farthest away.
So the moon's gravity is tugging a little bit harder on the side of Earth that's closer to it.
Exactly. And this difference in gravitational pull across Earth's diameter
Okay.
causes Earth to stretch slightly along the line connecting it to the Moon.
Wait, so the Earth is actually being stretched by the moon's gravity?
It's a very slight stretching,
Okay.
but yes. And this stretching creates bulges of water on opposite sides of Earth,
But right.
which we experience as tides.
Wow, I never realized that tides are actually a consequence of the Earth being stretched by the moon's gravity.
Yeah.
It's amazing how these forces play out on such a large scale.
It's pretty incredible. And tidal forces can also have significant effects on the rotation of celestial objects
Okay.
over very long periods.
Yeah.
Tidal forces can cause a moon to become tidally locked to its planet.
Tidally locked. What does that mean?
It means that the moon's rotation period becomes synchronized with its orbital period,
Okay.
so that the same side of the moon always faces the planet.
So that's why we always see the same side of the moon from Earth.
Exactly. The moon is tidally locked to Earth. And this phenomenon is actually quite common in the universe.
Right.
Many moons in our solar system are tidally locked to their host planets.
It's like a cosmic dance where gravity dictates the steps.
That's a great way to put it. Now, speaking of gravity's influence on celestial objects, let's talk about the Roche limit.
Okay, I'm all ears. What is this Roche limit all about?
The Roche limit is the distance from a celestial body
Okay.
at which a smaller object held together only by its own gravity will disintegrate due to the tidal forces exerted by the larger body.
Wait, so if an object gets too close to a planet or star, it can be ripped apart by tidal forces.
Exactly. The tidal forces overcome the object's own gravitational self-attraction,
Right.
causing it to break apart.
That's both fascinating and a little bit terrifying.
Yeah.
It's like there's a cosmic danger zone around planets and stars
Yeah.
where objects can be torn to shreds.
You could say that. And the Roche limit is crucial for understanding things like the formation of planetary rings.
Planetary rings, how are they connected to the Roche limit?
Well, one theory is that planetary rings formed when a moon or other celestial body wandered too close to its host planet and got ripped apart by tidal forces because it crossed the Roche limit.
So those stunning rings around Saturn, for example, could be the remnants of a moon that got too close and was torn to pieces.
That's one possibility. It's a reminder that the universe is a dynamic and ever-changing place.
Yeah.
And even seemingly stable structures like planets and moons can be subject to dramatic transformations.
Wow. This has been an incredible deep dive into the science of astronomy. We've covered so much ground from speed, velocity, and acceleration to Newton's laws of motion, the conservation of energy and angular momentum, gravity, black holes, tidal forces, and the Roche limit.
We have.
It's amazing how interconnected all of these concepts are.
It is.
I feel like I've gained a whole new appreciation for the complexity and wonder of the cosmos.
For sure.
It's truly humbling to realize how much we've learned about the universe, but also how much more there is to discover. We've given you a lot to ponder, listener name. We hope this deep dive into the world of physics and astronomy has ignited your curiosity and left you with a sense of wonder.
It has.
Remember to keep looking up at the stars and asking questions about the universe around us.
And until next time, keep exploring.